Yeah, okay. So these are the notes from last class. And we finished off with deriving the first Slater's rule. That is the expectation value of the one electron part of the Hamiltonian between two Slater determinants, the same Slater determinant. Okay? And we saw that every expectation value, that is whether it is H of electron 1 or H of electron 2, so whether it is 1 or whether it is 2, it gives me the same matrix element value, because the 1 is actually the variable over which we are integrating. So it does not matter. So it's a dummy variable and it does not matter which one it is. Okay. Now y'all had a problem understanding this last class, so I added this note afterwards to show that mathematically it is quite clear. But where it arises from is that the electrons are indistinguishable. And what matters is which spin orbitals are occupied, not which electron occupies which orbital. Okay. So that is, and we did this for the two electron case, but since you see that this is the same for every electron, we can generalize this to the n electron case, and then my expectation value of psi 0 with respect to any h is a sum over all the spin orbitals in that determinant. All the, okay, so if there are n electrons, there are n spin orbitals, and I sum the spin orbitals from 1 to n. So my problem is simplified. So instead of having to evaluate the wave function as a determinant, I can do it for individual functions and then simply sum it up. So basically, a product problem is converted to a sum problem. That simplifies things a lot. And we will continue from here with the next rule. So this is lecture 8 today. This is the first Slater rule that I have written. Then the next one we want to do is again an expectation value of the one electron part of the Hamiltonian, but between two different determinants. And how do the two determinants K and L differ? K has all same spin orbitals except one. Let's say the mth spin orbital is replaced by the nth spin orbital in determinant L. So K and L differ by one spin orbital. So let me write K now. So K is what we had originally, that is 1 by root 2 let's say chi 2 1. I think this is how I was writing it. And L is, let's say, 1 is the same, and chi 2 has become chi 3. So chi 1 1 is then contains is the mth. Sorry, chi 2 is the, so chi 2 is m and chi 3 is n. Chi 2 has been replaced by chi 3. This is again the 2 electron case. And then we will now try to look at the matrix element of only one particular electron. Then we have this. It's a bit time consuming to write these things, so this part of the lecture will be slow. But it's good to practice this as well. And have the patience to write everything correctly. Because often if you're impatient, you will make mistakes in some index and then all the rest of the steps will get messed up. Okay. No, these are spin orbitals, so Gx. So now we will do this again by inspection. Since we've done the first one explicitly, you will be able to see this. So this is half. And then we have the matrix element between chi1, h, chi1. Okay. And from the first two terms, so this one and this one, you have 2 and 3. So they are orthogonal. So this is 0. Then the first and the last term, so this and this is now again plus, and you have 1, so chi1, chi3, and what is left is chi2, chi1, so that is again, sorry, so that is again 0. Then I have minus. So tell me as soon as you think I'm making a mistake, because this is very error prone. Okay. Then you have again chi2, h, chi. So now I'm doing the second and the first, second from here and first from here. So this is chi 1 and then chi 3. That is again 0, right? Minus, which is, so that is now the first one and last one. So that is chi1, h, chi3, and then we have chi2, chi1.
Ma'am, this part is already done in the second term. You have put a plus sign in there, that should be negative.
Sorry. See? Thank you. Okay, so this is this. Then what I will.
The second term,
second and fourth is missing.
Yes.
So second and fourth is chi1, h, chi3, and you have
chi 2h, chi3.
No, again I made a mistake. Sorry. I am so sorry. It is difficult. Yeah, okay. So it's this one. So this is chi2, h, chi3, and you have chi1, chi1. Yeah. Okay.
Plus sign, ma'am.
Plus. Thank you. Thank you so much. Which means you are also paying attention. So I'm very happy. Okay. So this is, so now we have only one term left. So that is chi half, chi2, h, chi3. Okay. And then now if I do KH2L, this will also give me the same as we saw last time. So the full H, which is actually H1 plus H2 for the 2 electron case, that will be simply chi2 H chi3. Okay. So this tells me, so here you see there is no sum over any electron. So you only have one matrix element, the one which is between the two spin orbitals which are different. So the common one you don't have to evaluate at all. So then we come to so I can just write the general rule now, which is equal to MHN, where M and N are the orbitals which are different. So if there are two determinants which differ in one orbital, then the matrix element between them is just the matrix element of that particular spin, or those two particular spin orbitals which differ. So that is the second Slater's rule. Okay, this is number 2. Now we come to again number 3. So for 3, we will evaluate K, H, and L. So they are different spin orbitals, but both orbitals are different. So let's say in K, I have M and N, and in L, I have P and Q. Okay. So can you guess what will happen? If both are different for the 2 electron case. So what was happening? So basically by orthogonality, you were getting all zeros and only one term or whatever, some terms were surviving because of the same orbital being there in both the functions. But if neither of the functions have a common orbital, what will happen?
Be 0.
Yeah, it will become 0. So this you don't even have to work out. It is 0. Because you will never end up with an overlap. Yeah?
Sangita,
Yeah?
am I audible?
Yes, yes.
I think there is a confusion that in the last part when you're writing small h, you actually mean theta 1 on the final expression. Because
Yes.
you are
That is
using small h for one particle operator,
for
but the
one particle. Yeah.
final
This is the
summary is
sum.
actually sum of one particle operator. So I just thought I would clarify that.
Thank you.
Yeah. Okay. Thank you.
Yeah.
No. This right hand
This is
side
also, yeah.
theta 1 should be h. Because that's the one particle.
Yeah, that is only one. Yeah, that is just one.
The left hand side, it's a sum of one particle operator. So that should be theta 1. Yeah. That's now it is correct.
Yeah, this is correct. Yeah. Sorry.
Yeah, no, it's okay. Just a confusion because you are using small h everywhere. So that is why.
Okay. Yeah. According to the notation, the theta 1 is the sum over all the small h's, and small h is just for one electron.
Right. Yeah. Okay.
Thank you.
Yeah. Okay.
Yeah. So then that is that. So now we have evaluated the matrix elements of the 1 electron part of the Hamiltonian for the same determinant on the Bryan-Ketch side as well as different. By extension, of course, here I'm saying that both are different for the 2 electron case. But for the n electron case, you can always say that if the two determinants differ by more than one orbital, then the matrix element of the 1 electron part of the Hamiltonian. So even for the general case, so n electron case, there also it is equal to 0 if K and L differ by more than one orbital. So the language that is sometimes used is that uh, a one electron operator can only change the occupancy of one spin orbital. So this language actually comes from another type of formulation, which is called second quantization, which we will probably do a little bit later. But even for Hartree-Fock, this language has sort of permeated the literature. So you may have heard this sentence sometimes, that one electron operators can only change the occupancy of one spin orbital. So as soon as determinants differ by more than one orbital, then the one electron operator cannot make the occupancy same on either side, and hence the matrix element becomes zero. So this is a alternative language for the same thing. Okay. Or sometimes people say that one electron operators can only scatter one orbital to the other. So they're basically saying the same thing as Slater's rules. Okay. Now we come to the two electron operator, but before that we need to introduce some more notation in order to simplify our evaluation. So I will do that now. So you're familiar with the Dirac notation. Which is so some notation. Right? So here, and then if you write this, chi j. Okay. So this is the notation for the Dirac form, so the bracket form. And there is also an alternative notation. I think Professor Pal covered it, which is also called Chemist Notation or the Mulligan Notation. And that is the same for the one electron thing. But for the two electron part, it becomes different. This is the Mulligan notation. And that is okay. So it will be this. So these two will be for the same electron, and this two will be again for the other electron. So it will become chi I1, chi j star, chi j1, and then R1 to inverse, chi k star 2, chi L2. So remember the difference and how, and so basically when you have the chemist notation, then the first part belongs to electron 1, and then the first index in the first part is starred, and the first index in the second part is also starred. So you have I star and K star. So these are two alternative definitions. And you have to become comfortable with which integrals are equal. So then,
Ma'am, here xj should be start in the last line.
what?
In the last line, xj1 should be start.
No. This is the chemist notation.
Oh.
So in the physicist notation, the
Oh.
bra part, both orbitals are starred. This and this. In the
Uh,
chemist notation,
Actually,
maybe
please repeat that
Sangita,
part.
yeah, Sangita, it may be useful if you write the same integral in two different notation, like the IJKL
okay,
itself
yeah,
you write, so this will become IKJL. You understand
yeah.
what
So
I'm
this,
saying? So
okay,
Dirac
fine,
notation
fine. So
IJKL, you write Mulligan notation IKJL, then it will become easier because now you have changed the J actually.
yeah. Okay, okay. So when you're given an arbitrary integral, you can just think of it like first coordinates of first electron on the left and coordinates of second electron on the right for the chemist notation. But let's say if I want to write this particular integral in chemist notation, then this will become IK R1 to inverse IKJL. So it's the same thing in two different notations. So that has this same expression. So the chemist notation basically treats the first electron first. So chi I star, chi k. So for electron 1. So the important part is the first two orbitals are from electron 1. Then you have the operator and then you have the electron 2. It takes some time to become comfortable with interchanging the two
I think
notations.
there is a
If you
little
do it
confusion.
correctly, it will be fine.
Sangita, there's a little confusion on the second line when you're
Yeah.
writing the Dirac notation
Yeah.
IJ R1 to inverse KL, and the right hand side is chi I star 1, chi j star 2, then it should be
Oh, oh,
chi
oh, oh.
k1, chi L2.
Chi K.
So that is where there is a confusion, I think. Then it will be easier to. Yeah, sorry.
Sorry. I'm writing
Yeah,
so
that's
many
okay.
notations.
Yeah, I know, I understand. Yeah, okay.
I'm sorry. Yeah. So this is chi K and this is chi L. Yeah. Is that better?
Yeah, now it's okay. Yeah, it's technically correct.
Yeah. So in the physicist notation, you have the bra is the starred function and ket is the unstarred part. In the chemist notation, the first part belongs to electron 1 and the second part belongs to electron 2. So this is how you think about the two notations. Okay? And now we want to look at the symmetries. Maybe then it becomes clearer. Like which integrals are equal. So since you are more comfortable with the bracket notation, I'll do that first. So if you have IJKL, then since the integration is over dummy variables, you can simply interchange electron 1 and 2. So then you have JILK. This is easy, right? Then if you have real orbitals, then chi I star equal to chi I, chi j star equal to chi j, etc. So then you can have even more symmetries. So then this and this are equal. So IJKL, I'll just rewrite it, equal to JILK, and this is equal to KL KLIJ. This is equal to LKJI. Okay, and again by symmetry of the electrons, you have this is equal to, so these two are already equal, and from, so these four are fine, And here by realness, you have this is again equal to, no, I did that one. So what is left? So Lijk are again equal. Okay, so what is left now is when I am uh, conjugating one pair of orbitals but not the other. So then this is again equal to Li Jk. So L belonged to electron 1 and J belonged to electron 2. So electron 1. So if they are real, I can interchange them as well. So there you are. I think that is it. And there will be a JILK, LKJI, and ILKJ is also equal from here. Okay. So here again, I'm interchanging 1 and 2, and I get this. So you have all these 6 equal, and is there more? KJIL, and from here you have KJIL. So here I've taken electron 2, and because of realness, I can interchange the starred and the unstarred. So that is that there, and there is again interchanging electron 1 and 2, you have JK, Li. There. So these are all equal to each other. 8 possible integrals. And what have I used? I have used interchanging electron 1 and 2, and I have used real orbitals. So there is what is called 8-fold symmetry. Okay, so from the Dirac notation, you can see the 8-fold symmetry. The same symmetry you can see from the Mulligan Mulligan integrals as well. I will also do that so that you become comfortable with the notation. So if I have IJKL in Mulligan notation, then this is electron 1, this is electron 2. So interchanging electron 1 and 2 means simply KLIJ. And also, and now by realness, you can have little more. So by realness, we interchange I and J. So that is JILK, where I have interchanged both. You could also, from here also, I can interchange both. So that's LKJI. And then I can interchange one electron from here. Well, I shouldn't say interchange. That is by realness of one pair of orbitals. Then I have JI. So I interchange one and I leave the other the same, KL. And from here I can write LKIJ. Okay. And then again from here, Is there any place here? So this is again equal to KLJI, and this is again equal to IJLK. So this is again 8-fold symmetry. So finding out which elements are equal is not only useful from point of view of practice of notation, but it is also important when you compute things and code things. Because you can ensure always that you only compute things once and the other 8 you set equal. That saves a lot of computer time, and that is a very important part of all quantum chemistry codes. So this symmetry and identifying which ones are equal is very, very important. So now that we are aware of which are equal, we go back to again Slater's rule number 4. So Slater's rule 4. Now, this is the matrix element between the same determinant for the two-body part of the Hamiltonian. Okay, theta 2. So, and theta 2, if you remember, this is a sum over all unique pairs of electrons. Okay. So let's work this out. So I'm not writing the K again. I guess you remember. So K R12 inverse. This is again for the 2 electron case. This is equal to half, which comes from the 2 normalization factors. And then you have integration. I have to write this once more, unfortunately. So this is chi1 1, chi2 2 minus chi2 1, chi1 2. Okay. R12 inverse. Then chi2 1, chi1 2 minus chi star, and this is chi1 1, chi2. Oh, sorry, what am I doing? Chi2, chi1 2. Okay, and then dx1, dx2. So here
Ma'am,
now.
change the first term to in the second line.
Oh, actually, there's so much noise. Okay, yeah, thank you. Yeah, so now basically it's just a question of writing it in the proper notation. Here, as you can see, since this is a two-body operator involving both electrons, you will not have anything factored out which on which you can apply orthogonality or normalization or whatever. So you just have to just use a notation to simplify this expression, and that is just this. So you have half, and then let's write it in the Dirac's notation. I am more comfortable with the Dirac's notation anyway. So then this is this. So from the first and the first 2 terms from the 2 brackets, I have then, this is starred. So this is 1, 2, and this is 1, 2. Okay. Then from the second and first term, you have minus 2, 1, 1, 2. Then from the first and the third or first term of the second bracket, you have 1, 2. So this one, okay, minus 1, 1. So what happens? This is this. I actually find it very difficult to read terms when there is so little space. But I don't want to go to the landscape mode because then the PDFs become weird. So this is this, then this is this, then this, then we have this and this, and that is 1, 2, 2, 1, and then you have 2, 1, 2, 1. Okay? Fine. Now we just have to identify which two are equal here. So 1, 2, 1, 2 and 2, 1, 2, 1 are the same. So I can remove the half and I get 1, 2, 1, 2. And then from this and this, you have minus. They are also the same. So if you interchange, by interchanging coordinates of electron 1 and 2, and then you can write it as maybe 1, 2, 2, 1. So we have simplified the expression, and this is what is called the Coulomb integral, and this is what is called the exchange integral. We will look at why it is called so in later part of this class today. For now, let's generalize it to many electrons, and that is, and what will happen is basically you will just get a few sums. So for the general case, it is a sum over all unique pairs of orbitals of the same expression, which is ij minus ij ji. Okay, and if I now want to remove the restricted summation, so this is basically a double summation over I and j, where I and j are never equal. So you only have the unique pairs of orbitals in this sum. But if I want to remove this restriction, I can put a half and sum it over all I and j. And then what happens is when they are equal, then as you can see, I will simply cancel. So that creates no problem. And suppose when I is 5 and j is 6, then whatever value we get the same value when I is 6 and j is 5. And they are summed, so I will get twice what I want, and hence I have a half in front of it. Okay, so this is a general technique for removing restrictions on sums. This is also plays an important factor when you write a code, because if you have restricted loops, this cannot be converted efficiently to matrix multiplication. But if you have unrestricted loops, you can convert it to matrix multiplications, which are optimized in the code. So this is, it may appear equivalent and trivial, but when it comes to coding, these simplifications also matter a lot. So this is how it is written, and so this is the first Slater's rule for the 2 electron operator. Okay, then there is the next one. So 1, 2, 3, 4. This is the 5th rule. That is again when the 2 determinants differ by 1 orbital or 1 spin orbital. Then let's see. Do you have a piece of pen and paper? Can you try and work it out? If what happens if they differ by one spin orbital? Do you want to try it yourself?
Ma'am, give me some time. Give us.
Yeah, you are trying? Okay, okay. I'll give you 5 minutes, okay? All of you try.
Ma'am, I think we got this answer.
Okay. Okay, tell me.
It's actually from
What's
what? Means up to this one or um,
Yeah, just the two. Tell me the two electron case. Or do you want to tell me the
The
itself?
first term and the fourth term are same,
Yeah.
and second and third I think they are not same. I,
No, they are the same.
second and third term are same. Okay.
Yeah, just interchange. So you're saying second and third according to how I have written, or
Yes, they are same. They are same.
yeah, they're same. They're same. So then you get what? Again, the half is gone, and you get 1, 2, 1, 3 minus 1, 2, 3, 1. So it basically is the same. It's the same expression as before, right? Just 3 instead of 2. So there's nothing fundamentally different up to this point. But when you generalize, if you look carefully, you will not get a sum over all pairs, because now this 3 is, so 2 and 3 are different, right? So you cannot have, so this is, so 2, 3 pair is one particular pair. So the double sum will not come. Can you see that when I generalize what happens? So here what was happening is that 1 and 2 could be any electron. So it could be 1, 2, 1, 3, 2, 4, 5, 2, all pairs. So you would get this expression for everything, all pairs, 2, 3 pair, 5, 6 pair, 7, 9 pair. So for all pairs you would get this expression. So when I evaluate this for theta 2, I'm sorry, I again made the same mistake here. So this was, when I do it for theta 2, then I have to sum over all pairs, unique pairs of orbitals, spin orbitals. But when I have one orbital different, then 2 is replaced by 3, and this is a fixed one. So 1 can be anything. 1 can be 1, 1 can be 4, 5, 6, everything. But 1 cannot be 2 or 3. So 1 not equal to 2, 1 not equal to 3. But 2 and 3 are specific. The ones, the pair which is different in K and L. So my 1 can be anything. 1 can be 4, 5, 6, everything. But 1 cannot be 2 and 1 cannot be 3. So then when I generalize, let's see what happens. When I generalize, I will only have a sum over this one part. So let's say I call this I. Then I have I. And let's, okay, I will write it here. So let's call this I, and I call this M. So I M I N. So I have a sum over I, but my M and N are specific. So I have only one sum. When I generalize, it becomes different here, because you cannot have all pairs. that clear with all of you? Why the general expression is different?
Ma'am, please repeat the general part.
Yeah, so when you generalize, see, let's go back to the previous one. So here, how did we generalize? So we had 1, 2, 1, 2, 1, 2, 2, 1, and 1 and 2 can be any two electrons. Okay, so in my total Hamiltonian, when I have a sum over all unique pairs, then then my matrix element is also over all unique pairs. So theta 2 is what? So theta 2 is basically I not equal to j r rij inverse. So theta 2 is a sum of the Coulomb repulsions of all unique pairs of orbitals. And here also there is no restriction in because 1 and 2 are so one term is 1 2, another one is 2 3, another one is 5 6, another is 7 8, or 2 or even 2 5, 3 6, everything. So when I sum all the matrix elements, each expression is the same and it goes over all pairs of orbitals, spin orbitals. So this sum carries through from the operator to the integrals. But here you see, you have one. So electron number 1, it is the common orbital in K and L, and there are many common orbitals in K and L. So the sum will go over all the common orbitals in K and L. Okay, but the second index here, that is the 2 and the 3, that is one particular orbital which is different. So 2, so let's say the other orbit, if I have let's say a three electron system. So this we've done for a 2 electron. Let's say I have a 3 electron system. Then I have electron 1, 2, 3, 1, 2, and 3. Okay. No, wait. This if I use 1, 2, and 3, it will get confusing. So let's say I have IJM. So I have IJM in K, and in L I have IJN. These are particular. No, no, let's see. What is an even better notation? Let's not use I and J. Let's use AB. So these are particular orbitals. There's A, there's B, there's M. There's A, there's B, there's N. So when I'm evaluating the 2 electron matrix element, then I am evaluating, I will get one expression which is AM, AN minus AM, NA. I will get another one which is BM, BN minus BM, NB. Okay, so I am summing over the common orbitals. But this M and N, I cannot have, let's say, M. If I do M, N, this is 0 by the property of determinants. If I do N, that is also 0 by property of determinants. So I cannot, so M and N are not dummy indices. They are particular indices. They are a particular index. You cannot sum over them. well, let's see how to put it. How else can I explain? If you go through the general
No,
derivation, yeah.
that's fine. I am asking that you write in IM R1 to inverse IN. But how? So why you write here R1 to inverse? IM IN like that. So
Oh, you're saying why I'm writing R1 to inverse? Because this is like just electron 1, electron 2. So when
no,
I'm
no.
using Dirac's, no?
In normal case, you are using IN. Uh,
So 1, 2 are basically the electron coordinates.
no, okay, that's fine. I
Okay.
mean, and this minus part, 1, 2, 3, 1 part.
Oh, okay. No, that is just that is I've just not written it. There is no problem there.
Oh, okay. I'm confusing that part.
Oh, sorry. I am so sorry. This is I am R1 to inverse Ni. That is there. That is there. That has not gone away.
Okay.
Actually, this also has a shorthand notation to avoid forgetting. So that is just I am, two lines in. So this is a shorthand notation for this whole expression. Just like if you don't write R1 to inverse, that is also, so here see I'm not writing R1 to inverse. You, it just means that there is an R1 to inverse. That is part of the notation. So when I write this, it actually means that the R1 to inverse is there. So quantum chemistry is basically a lot of notation, and if you keep doing it, you get comfortable with the alternate notations. But initially, it is very confusing. I totally sympathize with you. So this is not an overlap. So when I'm not writing R1 to inverse, R1 to inverse is actually present over here. There is R1 to inverse over here. There's R1 to inverse over here. It's part of the notation. You may or may not write it. Again, when you put these two lines over here, it means that you have the Coulomb and you also have the exchange. And the exchange comes with a negative sign. So it's all just notation. As long as you're clear what everything means, I think you will figure out what is happening. And when you start using many different notations, you'll see even I am not being very consistent. I am sorry about it, but it's just that it has really got into me. And so whenever I see a line, I identify that there is an R1 to inverse here. But for you, it may be confusing. You may think this is like an overlap matrix or an overlap quantity, but it's not. There is an R1 to inverse over here. Okay. So this is about it. So okay, no, there's one more last Slater's rule, which is that this is number. So this was number five, I believe. Yeah. So this
Madam,
is yeah.
just to be clear, in the fifth Slater rule, you
Hmm.
wrote the expression. Can I go to that? Yes. When you wrote the K R1 to inverse L in the bracket notation, and you wrote the second line, that is 1213 sandwiched or 2113 sandwiched, etc. You
Hmm.
only you only use the notation. You did not apply any such integrals, right?
No, I did not apply anything. I only applied the symmetry of integrals in this step, and that's it.
Okay. As R12 takes account of both the initial and the final state, you did this right.
Yes.
Okay. I was confused about that. That one
No,
orbital would be separated, or okay. Thank you.
no. Here, so when it's like a two-body operator and you have only two electrons in your Slater determinant, then nothing will get removed. But if you work out the three electron case, if you have the patience to do it, you will see there again the orthogonality will play a role.
Okay.
because the third orbital will come in, and
Okay.
some terms will become zero and some will survive because of the common extra orbital. But
Okay.
it's a very long procedure, and well, you can try it at home, but it will be very long if I try to work it out here.
Okay. And also the, I mean, the R12 inverse is already there. You are not writing this in the bracket
Exactly, it's
notation.
always there. Yeah,
Okay.
it's
Okay.
when you write these integrals in the context of quantum chemistry, that R12 inverse is implied.
Oh, okay.
But
Okay.
sometimes again they are overlaps, so you have to be careful of the context.
Okay. Okay. Thank you, man.
Yeah. Probably if you follow the book, they are more consistent than I am because I am doing it live, so I sometimes neglect it. But you will also find that they have also neglected to write R12 inverse in many, many places in Zabo and Oslo.
Okay. Yeah.
Yeah, and there is a general derivation of Slater's rules, like for n electron determinants in general, using permutation operators. Uh, you can read it if you are curious, but you will not really require it later on. But then it becomes clear what happens for uh, like 3 electron case and 4 electron, etc. Because there is one more last rule, that is when you have k theta to L and k and L differ by more than, oh sorry, there is actually differ by 2 electrons, then the rule is, I will just write it, okay, I'm not working it out. I guess you get the picture that that is how it goes. So the derivation is not, I'm not doing it. So you have k theta to L, that is equal to uh, so now the sum will disappear and you will only have mn pq, where mn by two careful, two spin orbitals. Two spin orbitals. So Mn replaced by Pq. This minus P is equal to Mn. Okay. So when they differ by two spin orbitals, the sum over I over here also disappears, and you only have one matrix element. So direct and exchange. And if K and L differ by more than two spin orbitals, then K theta to L is simply 0. So the eventual rules are not very difficult. So the more the two determinants differ, the simpler the expression. So for one electron operators, if it's the same determinant, you have a sum over all the electrons. If they differ by one spin orbital, you have only one matrix element between the two different spin orbitals, and anything more and difference of anything more than one spin orbital, you get 0. For the two electron part of the operator, if they are the same, you have a double sum over I and j. If they differ by one spin orbital, you have only one sum. If they differ by two, you don't have a sum. And if they differ by more than two, it's 0. So the eventual rules are simple, and we will keep using them. So now, okay, so now since this is a tutorial class, I thought I will give you an exercise. Perhaps it will take you maybe 10 minutes. I don't know how long, but you can try. So do you have Zabo and Oslund? Have you all managed to get the PDFs? Hello?
Yes, ma'am.
You have the Zabo and Oslund? Okay, then I can just tell you the exercise number. Is there anyone who doesn't have? Okay, I can share the screen afterwards after I find the page. So its classwork is exercise 2.13. And I will find that exercise and share it on the screen in case some of you don't have it. So let me see. This is actually you can stop the recording now. I think you don't need the tutorial in recording mode. So let me see. This is 2.13. Hmm. So in this expectation value, do you understand the notation? What is psi AR? Psi AR is when A has been replaced by R.
Ma'am, what is this size?
Yeah, so these sides are basically single determinants where they have the same orbitals, like the size on either side. They have the same orbitals except in the bra side, A is replaced by S, by R, and on the right hand side in the ket, B is replaced by S.
So what does ABRS signify? That I cannot get.
They are the spin orbitals in the determinant.
All four. Yeah. Or
Yeah,
ARBR position
yeah.
and RRS.
No, they are all spin orbitals. Psi AR means that in psi, let's say it has A, B, C, D orbitals, spin orbitals. The A spin orbital has been replaced by R. So you
Okay.
can consider like a parent psi which has A, B, C, D, E, F, and in for the bra function, A has been replaced by R, and for the ket function, B has been replaced by S.
Okay.
So this is what is called excited determinant. So there is a ground state. You can think of it. There is a ground state which is ABCD, and psi A to R is one excited state, and psi B to S is another excited state. Or they may be the same if if A equal to B and R equal to S. So the first part, I guess all of you have done. That's easy. Can you tell me why the first part is 0?
Overlap of orthogonal orbitals. That is that, that term will come up.
Okay. Well, you could just look at Slater's rule directly. You don't need to work it out. You just need to see if they differ by more than one orbital. So for the first part, does anyone have a problem with the first part? For the subsequent parts, like for example, the negative sign in part 3, you will need some additional knowledge, which I have not told you about yet. So if you are stuck there, you can just stop. I can then tell you why that negative sign is coming. So the first part should be clear to everyone. So what is happening is, so you had the same determinant, some ground state psi with ABCD, like I said, and in one for the bra function you have replaced A with R, and for the ket function you have replaced B with S. So basically now the two functions psi A to R and psi B to S, they differ by two orbitals. In the bra function, A is gone and R is present. So you have, but B continues to be present. And in the ket function, A continues to be present, but B is gone and S is present. So you have B and R in the bra and A and S in the ket. So the bra and ket differ by two orbitals. And this is the one electron part of the Hamiltonian. So the matrix element is 0 by Slater's rules. So the first part doesn't require you to work out anything. Then the second part is also straightforward. Can someone reason it out for me? Let me see. Rishabh? It is unfortunate that I cannot figure out who is speaking when. So if there is one of you who has never spoken till date, please tell me how to work out part 2. I guess you will know if you have not spoken yet. Anyone? No?
Ma'am, first part I didn't understand.
First part you did not understand. So the basic logic of the first part is that the bra and ket functions differ by two spin orbitals. So which two? So let me see. Maybe I can write over here as well. Okay. Okay. So here, let's say I had A, B, C, and here I had also A, B, C. Then psi A to R means I have R, B, C. And B to S means I have A, S, C. So then the bra and ket functions differ by two spin orbitals. That is R and B on the left side and A and S on the right side. And since this is a one body operator,
Understand.
yeah, it becomes 0. Okay? Because here A not equal to B, R not equal to S. Now, in the same situation, if I put A equal to B and R is not equal, so let's say I replace B by A. This is horrible. Okay, A. Then now what do I have? Then I have one orbital different in the two cases. So you have RHS. Okay. Oh, sorry. This was not right. So for the second part, A not equal to B, A equal to B means I am replacing A by R here and A by S here. So now I'm doing the second part. Okay. So for the second part, this is the first one, RBC. Okay. And I have ESC on the right. Then here I have A replaced by R over here. So RBC. And here I have A replaced by S. So I have RAC, SAC. Okay? RAC and SAC. So there you have one orbital difference. So you have the matrix element between R and S. So part 1 and 2 is clear with everyone. Is it? Because I have something new to say for the third part. So I want your attention for the third part. One and two is clear? And anyone has a problem? So can I do part 3 now?
Can you explain the C you brought in the first and the second part?
Oh, I just wrote, I mean, here they don't tell you how many electrons are there, but I've just assumed that there are 3, just to write some more orbitals.
Oh, okay.
Because they don't tell you it's a 2 electron or 3 or 4. I mean, I could write D, E, F, whatever, however many I want.
Okay, so in general, you assumed another orbital that is C.
Yeah, I just wrote one more for generality's sake.
Okay.
Ma'am, here why you are saying that is a one body problem means
Oh, because it says theta 1 over here.
no the theta one. Okay, so theta one
That's the
equal to
one electron. It's not a one body problem. It's the one electron part of the Hamiltonian.
and that is why no spin cup part are coming.
Spin part is there. These are all spin orbitals.
No, no, means the in the previous cases like I R1 to term this theta 2 the terms
That is theta 2. This is just
that
theta
is
1.
not
This is,
coming. That only we are considering theta 1 here.
yeah, yeah. They have, the question says theta 1 only. So it's just
Yes.
one body, one electron part of the Hamiltonian.
But all terms will not be zero when we consider the total one.
When you consider the total one, no, it will not be 0.
Madam, it would be helpful if you write explicitly the expression of psi AR and psi BS, that one.
Actually, I can't write it because I don't know how many electrons are there.
Oh, okay.
You just have to think about it. You can, at most, I can write, like a string of occupied spin orbitals.
Oh, yes,
For
yes.
one, yeah, because the matter. I mean, this is a determinant, of course. It is a determinant of some size, of
Yes, yes,
size of
and you
orbital.
don't know the size actually.
I don't know the size,
Yes.
and then I don't know the normalization factor. And anyhow, that does not matter. That is the point. That as long as you know by how many, it can be like 1,000 electron system also, but they only differ by two orbitals, so it's 0. But or they only differ by one, so I know the value. Or they don't differ and I still know the value. So that is the benefit of having these Slater's rules. The common orbital cease to matter, except in the uh, expectation value of for when the bra and the ket are the same. But then also it's just a sum. So you can imagine if you want to write it, like expand 1,000 by 1,000 determinant, that expression is horrible. But simply increasing one index on the summation, that is not difficult. So this n can be 1,000. Then I cannot write psi anymore. But this expression is still easy to write.
Okay.
Ma'am, in the part 3, are we going to assume that switching between two spin orbitals give a negative sign? Like that?
Exactly. Exactly. Excellent. Who is this, by the way?
Doi payon.
Okay.
But why this thing happened?
Why
Yeah.
this?
Means
This
I
is
am just back calculating to get the answer. And
yeah. Well, at least you have hit the operational part of it. So why this is happening is because um, so this is actually anti-symmetry at work, which is why we have chosen the determinant to represent it. And there is a principle which is part of Slater's rules, which I have not mentioned till now. That is, it is the principle of maximum coincidence. So before you apply Slater's rules, all the common orbitals have to be in the same order in the two determinants that you are comparing. So the common ones have to be exactly in the same order, and you have to switch the spin orbitals in the determinant and change the sign accordingly till you get this same order of common orbitals, common spin orbitals. And then you can compare the different ones. So that is part of Slater's rules. I will add it to the notes as well. So I was waiting for someone to get stuck there. But you also found the solution or the reason, so that's very nice. So that is the principle of maximum coincidence, which is part of Slater's rules, which says that all common orbitals in bra and ket functions must be in the same order. If not, we must rearrange with appropriate sign change. And what is the sign change? That is basically for every switching of spin orbital, we get a negative sign. So it's a simple rule, but it's an important rule. Is it clear to everyone? And then, okay, let's see how we apply it over here. Then it will probably make things clear. So here now what is happening? So A is not equal to B. So I had A, B, C in order. Okay, and I have replaced A with R. And B and C remains the same because B is not equal to A. And I have replaced B with S, but S is R. So I am writing A, R, C. So now on the in the bra and ket, my R is in a different position. So I have to switch it. So I can switch either one. Let's say I switch. Well, okay, let's switch the bra. Then I get minus BRC ARC. So now the common orbitals are in the same position, and now I can write my matrix element between B and A. So that is the third part. Is it clear? Everyone has got up to the third part. So who is working on the fourth part then? Anyone who started on the fourth part? So in the fourth part also you will need this principle of maximum coincidence. Okay, I'll wait till 10:50. So that's 4 more minutes, and then we'll do the fourth part together.
Ma'am,
Yeah.
in the second part, can you please explain again that why it is SAC not ASC? Like,
Oh, because Because we replaced B with S and B is equal to A. That's
But
why.
we can why we cannot replace it in the other way around? Means first we replace with means ABC and ABC. We can replace to a AAC and AAC. Then we can actually get the information.
Yeah, you can you could have done it the other way, but answer would have been the same. So you could have where should I? Okay, I can put a star here. So then it would have become ARC and ASC.
No, but I can get RAAC
Uh,
in some way. Means I don't understand what I should replace after what.
um, okay, so tell me what you are getting.
So suppose in the first step in the
Yeah,
brown part, you I write ABC. From there I get RAC.
you get RAC.
In the second and in the cat part from ABC, ABC that I can write uh, ASC because B is replaced by S.
Mm, no, but then if you write B is A in the bra part. So if you write B is A, then then you must replace A with R.
I mean, which replace I should do first? A to S and B to R, or this condition I should apply first?
Uh, so here basically what they mean is that the orbital which is involved in the change, they are putting the condition on that orbital. So if you replace, because what would happen if you replace B with A first, then you end up with two A's,
Yes,
right?
yes, that is that I am asking.
So that would have become zero.
Yes,
So that is not a valid way of doing it. I mean, because you cannot have like two same spin orbitals in the determinant. That is one way of thinking about it. Because at any stage, if two orbitals become equal, then they become zero. So that would not be valid. So you have to sort of replace A again with R. And also, even if you say that, okay, even if you don't consider that and you have AAC, then when you put R, then you don't know which A to replace with R.
now what I did at the first step is that I replace A with R in the bra portion. I replaced A with R and then I get RBC
Hmm.
from and RBC is equal to RAC,
RBC is equal to RAC.
and in the right part I have ASC, and, and I missed here.
Yeah. Okay. I understand what you did, but it sort of implies that in between you have two A's. So that is so what it basically, okay, maybe it's not so clear in the question, but I guess the conditions are on the orbitals which you are changing. So here basically you used the B equal to A on something that did not change, that wasn't replaced. So when you replaced this, so that was not necessary. If you do that, then you will end up with the negative sign here, which is
Yes, minus RAC,
Yeah.
minus RHS.
Yeah.
Get,
I
but
think what
I
they
don't get.
mean is that you don't understand how to decide, right? Okay. Uh, so what is the best way? The best way is that you only so when there is a condition, you apply it to the orbitals which are changing. Don't touch other things. So
Can you please show again that how you get that SAC, not ASC?
how I get SAC? So how I get SAC is I replace. So what they tell me is A is equal to B and R is not equal to S. Okay. So I want to replace A with S. And then I put B equal to A.
That is why.
That is what you have done on the bra side. But you did
Yes.
not follow the same procedure on the ket side. So basically, if you were consistent in how you replace things on the bra and ket, you would again get the correct expression. Isn't that so? So if you did the right hand side in the same way, then you would also get SAC, and you got RAC on the left, so you would be fine. So you would get if you but you followed like two different replacement procedures on two sides. I think that caused the problem. So if you always replace A with R and B with S first, and then you changed the other one. No, you have a valid point. It makes a difference how you do it. So what would be the
Sangita,
yeah
can I say one thing? Just
yeah
take,
yeah yes please
yeah, can I just take 1, 2, 3 as ABC.
yeah
So you construct an R let be 4 and S maybe 5. So you construct IR as 4 and A is equal to B. So let's say 413, and there it becomes 153 if S is 5. Okay. So his point is 413 and 153. If you want, then it will become a negative sign. So just check out if there is an error in the exercise.
no actually it's not an error in the exercise, it's just the order in which you do the replacements
Yeah,
that makes a
but if
difference.
A is equal to B, that means 1 is equal to 2.
Yeah,
So
so but that you cannot do
let's say I
anyway.
start from 1, 2, 3 and replace 1 by 4. So that gives you 4, 2, 3. Okay. And there it becomes 153.
Yes,
4, 2, 3, 153. So
153.
1 and 2 are equal. So it basically becomes the same orbital, but then you want to bring you have to do an interchange on the right side to bring it in the same place, RNS.
Yes, but you could also have done it the other way around, like I did, and then you would not get the negative sign.
Yeah, which way? Which is the other way now?
The other way around is uh, when you replace A with R
Yeah,
for
so
the
I get
graph
413 or 4.
4 1. Yeah.
Yeah. And
You
then
get
this side will be,
413,
and that
and then
side will be
you get
153.
513.
How it will get 513? Because B is replaced by S, right?
Yeah,
So 5 will not
but
come
there
in the
you
first
consider
column.
A
5,
is equal to B. So basically, what they mean in the question is that the position at which you change the occupancy is different for the bra and the cat.
yeah, so in the first position you are changing 1 to 4,
Yeah.
and the second position you are changing 5. Right, the rest are same. So once you try to bring it in the order, then there is an interchange. Where you see in the first position now R has come, and in the right side in the second column S has come. So except that here
Yeah.
it is B,
Then
there is A, but B is equal to A.
yeah. So you could have replaced A as well. So that, I think that was the point of the thing. But
Just
but I
check
but I
up
can
this.
understand that there is a confusion here.
I would say just check up. See, you got SAC.
Yeah, because I replaced the first A because A is equal to B.
Yeah, but still,
But I could have replaced the
yeah.
second one as
So
well.
I
I
think
get the
no,
point. But
I think the sense is that you have to replace the second one. That's the meaning of that psi BS.
but then there will be a negative sign.
Yeah, so that is where I'm saying
Yeah.
just check up this problem. I'm not saying the problem is wrong, but I will also see whether the exercise answer is right or not. And check up the other one also in the same way. Whether they have goofed up the sign.
So actually, even in the fourth part, I think then the same problem will crop up. Maybe because it matters which way you do it.
But just check up this, I think.
Okay, I will check
You
it
can
out.
check up. I'll also
Yeah.
check up and then get back to them. Yeah? I'll tell you.
Yeah. Sure. So did all of you get the point, or?
Ma'am, we have to look about the notation. Means it's getting really confusing with the 1 electron and 2 electron thing.
The one and the two electrons. So
Yeah,
here you
means
are only
like
talking
in
about
this
the
case,
one
if
electron. In
it's
this
1 electron
exercise, there
thing.
is no two electron.
Hmm. So that's why we're writing like this A B C and ABC, like in the bracket.
Yeah, so I'm just using like a rough representation. This is no particular notation. I mean, what this is a determinant.
Okay.
Yeah.
Okay.
But just to
Like
indicate
I'm
like
really
which
getting
orbitals
confused
are
with the like.
present.
Okay, like I really did with the 2 electron thing. Means I didn't realize that there's a 1 electron thing, and like I've done with XR and XA like that.
That's also fine as long as you can keep track. But if you write all the sky and everything, it
Okay.
becomes so many notations, then you get confused.
Hmm.
So all of quantum
Yes, ma'am.
chemistry is
Like
like this. I mean, you have to simplify the notation, but you have to keep in mind what it means and what is hidden. So it's a bit
yeah.
tedious with the notation. Okay. So then maybe you can all try 4 and we'll part 4 as well. And I will get back to you regarding what they exactly mean with this notation, like what they mean by A equal to B or not equal to S, and if there is a mistake. And part 4, you can try, and if not, I will work it out next class, which is then on Thursday, 9 o'clock. Okay, so let's finish here today. It's 11 o'clock.